Welcome back everyone. In this video, we are going to discuss about Module 3 of our ITN course, which is Protocols and Models. So let's get on with it. So this module, as I specified, it covers the details about what do you mean by protocols, what are the different types of protocols that we have, what are the different reference models, why do you need a reference model, why is it so important that you study networks from a network model perspective. So all these things we shall cover in this particular module. So this module has got the following objectives. If you can see, these are the things that we are going to cover here. The first thing being, what are the rules, what are protocols, what are the different protocol suites, or what do you mean by a protocol suite, what are the different standards organizations, what are the different reference models, what do you mean by data encapsulation, and how do you access the data, what role are actually played by the addresses when you want to access the data. So these are the things that we are going to cover in this module. This module is pretty important because it covers all the fundamental basics behind the scenes of a network communication, starting from basics of protocols and setting up of the reference models. All these things are covered in this particular module. So let's go on. As most of you are aware, there are the three fundamental things for any communication to happen. The first one is you need to have a sender, you need to have a receiver, and for the sender to send something, you need to have some kind of a channel, which we call it as a median. This is what is depicted here. We call them as a source, destination, and the channel. Source are in our discussion. Let's say that the sender can be anybody. It might be people, or it might be an electronic device, or it might be a server. It can be anything. The receiver also can be the same person. And channel is something, or it is a kind of media that provides a pathway for this message to travel from the sender to the receiver. And let's go for the network protocol requirements. Now, what if when everybody is talking about reference models and protocols, there are some things that you need to understand. That why do we need protocols first? Why do you need to that? For that reason, now for a message communication to happen in the proper manner, these are the following things that are need to be taken into consideration. The first thing is something called as message encoding. It's pretty simple. Encoding is something of converting information into another which is acceptable for transmission. The best analogy is, if I want to convey something to you, I have to put it into English, then I should talk in English so that you will be able to listen and understand what I'm trying to say to you. That is encoding. I'm talking in English. So converting whatever information I want to transmit to you into English language and sending it to you. Message formatting and encapsulation. This is the same thing once again. So here when I'm talking to you in language, in English, there are some particular words and the speed at which I talk. All these things, and even my pronunciation, all these things that comes under your message formatting and encapsulation. So this completely depends on the type of the message that I'm transmitting, and also the kind of channel that I'm using to transmit that message. And the third one is message size. If the message size is huge, can you send the large message at a single time, or do you want to break it down? So the message size plays a crucial role when communicating. And next one is the message timing. Message timing is to do with the synchronization between the sender and receiver. If I am talking at one point and if you're listening at other point, it doesn't look good. Now, if you're watching a movie with subtitles which are not in sync, so you listen to something, but you can see the language or the subtitle of something else, so which is very odd. Similarly, message timing is very crucial for network communications. That is the reason we have a lot of synchronization mechanisms to keep both the sender and receiver in sync all the time. Last one is the message delivery options, where we already studied in the earlier videos that there are three types of message delivery options. The first one includes unicast, one-to-one communication, multicast, one-to-many communication, and broadcast. Broadcast stands for one-to-all communication. So these are the basic requirements for any protocol to get the job done: encoding, formatting, encapsulation, size, timing, and the delivery options. Now let's go into the protocols part. Once we say protocol, there is no one protocol that does all the job. It doesn't exist simply. So there are lots of protocols so that we can group them together based on the type of work they do. According to that group, if you see, the network protocols define a common format and rules for exchanging messages between devices. So these protocols are actually implemented by the end devices and also the intermediary devices. These protocols can be done in software, hardware, and both. Okay. The most important thing is each network protocol, whatever protocol you are saying, has got its own function. It's predefined, its own format, and its own rules for communication. So if you need to use that protocol for this, you have to follow its rules agreed upon the standards. Now, as I told you, there is no one protocol which does all the work. So for that reason, we have different protocols which does their own specific work. In order to group them, if you can see, these are the different protocol types, most common protocol types that you observe. The first one is which comes under network communications. The second one is network security. The third one are routing protocols, and the last one is service discovery protocols. To just give you a brief about these protocols, what they do. If you talk about network communications, these network communication protocols will allow you to communicate with one or more networks. That means it can allow you to send and receive messages with other devices. Network security, as I said, it's a major concern, and all the protocols that come under this category are there to provide your basic CAA triad abilities. I told you about the CAA triad earlier: confidentiality, integrity, and availability. These are the three main functionalities or requirements for network security. The third one is routing. Once again, when you are transmitting from one network to another network, routing plays a crucial role, because your router has to decide which path it has to take, how to forward the packet onto the next destination. So all those protocols which help to make the decision comes under the routing category. The last category is called as service discovery. This is too much like DHCP and those things, which will provide you an automatic IP assignment, neighbor discovery protocols to find out if you switch on your Wi-Fi, it automatically show you all the networks, right? So it has to contact the access points. It has to give you the particular information. So all those types of protocols comes under the service discovery protocols. These are broadly classified. These are not the absolute. These are only, I don't say that these are the only categories, but broad classification gives you for network communication, security, routing, and service discovery. Okay. So what does these protocols do? Now I told you about the categories, right? So what does these protocols do? What is this main functionality here? These actually, the protocols play a role in such a way that when I'm discussing with you guys, when I'm talking to you, we both agreed upon the English language. So my pronunciation, my way of speaking the language is quite okay for you to understand. But if I choose some other language, my own language that you can't understand, there is no purpose of for both of us to communicate. Whatever I'm speaking, you don't understand. Okay. So these protocols play a crucial role in such a way that the devices use these agreed upon protocols to communicate with one another, because we are human beings who communicate through our voice and you can listen to it. But these are all devices, they only communicate through ones and zeros. So we have to have a predefined standard or some set of rules that govern this communication between these devices. So what are the different functionalities that these protocols need to do? These are the most common functionalities that any protocol needs to implement. So where we discussed about the categories of protocols in the earlier slide. In this slide, if you talk about, the first thing is addressing. So addressing is very important, because unless until you identify who is your sender, who is your receiver, you won't be able to communicate. The second one is reliability. Reliability comes from, if you want to send some registered post, you will get an SMS back saying that, sir, your message has been delivered, or in your SMS delivery reports like that. You need to have a reliable network. Reliability comes from the point where your delivery is guaranteed. Flow control we discussed earlier. It is more to like we want to regulate the data flow in the network. We don't want a fast sender sending out a data rates at high speeds to a slow receiver. We want to regulate the flow such that it goes normally. And sequencing is to do with the allocation of sequence numbers to each and every unit of data that is going on the network. Next comes error detection. So error detection also tells you if your received data contains any errors or not. You should be able to identify whether the data that you received is the same that the sender has sent or not, or it has become there are different ways why the data might have errors. We will discuss it in the next module. And the last one is the application interface. Application interface is to do with where we can interact with the system, where we want to send a data, where you can see an email client or even your Facebook or whatever, the web pages that you see, all of them comes under your application interface, even the FTP protocol, where you are allowed to download something from the internet. So you have to have an interface for the human being or for the user to interact with the system and to use these protocols to get the job done. Okay. So these are the common protocols that we use in TCP IP protocol suite. We will discuss about the protocol suite in the later part. So I'm just quoting you the example of these things. Now, for a message to be transmitted from one system to another system, these are the most common protocols that we use regularly. So let us say that if you are using your web browser, the first protocol that you encounter is the HTTP protocol, which is an hypertext transfer protocol. The next one you encounter is the transport layer is your transmission control protocol, TCP. and then your network layers protocol IP, internet protocol, and the last one is the Ethernet. And as I said, there is no just one protocol that guarantees your delivery or that does all the transmissions. No, each and every one of these protocols are to be used at different stages of the network communication. So in order to understand why do we need so many protocols, why do we need these different protocols to work in different stages, we have to understand the concept of layering and also the usage of reference models in networks. So let's go there. So let's come to the protocol suite. What do you mean by a protocol suite? What do you understand by this term? So protocol suite is nothing but it's a collection of protocols. That's all. As I told you, we don't have just one protocol. We have different protocols working at different layers. So what are these layers? So whenever I talk about protocols for communication, I say that these protocols are actually used in different layers, where the layers are stacked on one above the other, higher layers, lower layers. Those are the terminology that we use here. Okay, so protocol suite is nothing but a group of interrelated protocols necessary to perform a communication function. So protocol suite means usage of each. I mean, as I said, if there are 4 layers to communicate, so at each layer you use one particular protocol. So the protocol suite will contain all the protocols from these different layers. I'll show you an example. Don't worry. As I said, whenever we talk about a protocol suite, we talk about higher layers and lower layers. So let's go into and see. Now, the most commonly used protocol suite is the one which we are using daily, which is the TCP/IP protocol suite, transport control protocol and internet protocol. And the most common name for this is the internet protocol suite. This is used by millions every day. There are the other ones called as the OSI, Open Systems Interconnection. Here the open system is going to tell you that the system which is open for communication, that is it has the capability to send and receive messages through a medium. The third one is the Apple Talk. It is the proprietary suite released by Apple company. The fourth one is Novel Network. On top of this, there are some others also. There are some protocol suites which are used by Cisco, ADP, etc. But still, the most commonly used one is the TCP/IP protocol or the TCP/IP protocol suite. If you see here, if you see the protocol suite here, I'm showing you now. This is called the TCP/IP protocol suite because it tells you all the different protocols that can be used at each layer. If I say this is 1, 2, 3, there are 4 layers in your TCP/IP protocol suite or the internet suite. And what are the different types of protocols that are to be used at each of the layers? This is the protocol suite for TCP/IP. Similarly, if you take OSI, this is the protocol suite for OSI model. So if you come across the term protocol suite, please do not get confused. It is nothing but collection of all the protocols which can be implemented at different layers of your network model. Okay, so these are the most common ones. And let me say, if you go into the TCP/IP protocol suite, these are all the different protocols that we have. If you can see, application layer has got huge number of protocols with DNS, which we use commonly. DNS for email, you have SMTP, POP3, IMAP, for file transfer, FTP, SFTP, TFTP, and even for the web services, HTTP, HTTPS, or REST APIs, the DNS, and in transport layer, the TCP model, the TCP protocol, which is connection oriented, and the UDP protocol, which is connectionless. And at the network layer, of course, network layers, the only protocol we use is IP, the most important protocol. We have 2 versions of IP, IPv4 and IPv6, which we discussed earlier. And there are other protocols, we call them as sister protocols to IP, which help for efficient implementation of your IP protocol, which are like ICMP version 4, ICMP version 6, ICMP version 6, neighbor discovery. These are the routing protocols most commonly used across the network: OSPF, EIGRP, BGP, network address translation, NAT. And finally, we come to the bottom layer, which is your network access layer, where we have ARP, Ethernet, and WLAN protocols. So this is the basic overview of a TCP/IP protocol. So most of these terms and most of these protocols are covered as part of your computer networks theoretical course. So if you want more information about these things, we'll be covering them at the later stages when we discuss in depth about TCP and IP protocol. So, but as I said, it's not right for me to discuss all these things because it will be a very lengthy video. If you want more about these things, we will be learning later on. But if you are so much interested, just go on with the textbook, go on to Google platform and search for these. You'll get huge amount of information, very valuable information on these protocols. Okay. So what is this communication process? Now, if you see from the, let us say that I broke it into 2 parts. One of them is the web server and web client. And this is how it happens. Whenever you want to send a particular data, the first data is sent on to the application layer. Application layer forwards it or sends it to the bottom layer, which is the transport layer, where another header is added. and this particular goes down to the next layer, which is the network layer, where an IP header is added, and finally it is forwarded to the bottommost layer, which is your data link layer or the physical layer, where a Ethernet frame header is added. And all this process of adding up of headers at each and every layer is called as encapsulation process. So this is how it goes, and the same reverse thing is followed at the receiver. It is called as decapsulation. Okay, so when a web server sends a web page, what your client does is it checks out it decapsulates. That means it removes the first Ethernet frame, and then it checks the IP address whether it is right or not. It also checks the checksum, and if it is okay, it removes this IP header, and then it forwards to the transport layer. The transport layer once again verifies with your TCP protocol whether all the information provided is perfect or not. Are there any transmission errors? If everything is good, it removes this layer, and then it forwards the data to the application layer. That's where you can see your original web page. So this process of adding up the headers at the sender side is called as encapsulation, and the reverse process of removing of these headers at the receiver side one by one is called as decapsulation process. This is how usually the communication happens, and all the things like whenever we talk about network communication, these headers will be added, and there is a packet tracer activity video which will show you these encapsulation, decapsulation processes in detail, and also the header formats. I will make a video with that particular PT activity where you can get good information about this particular. You will be able to understand better rather than just looking at the theory part here. Okay. So who owns the internet? I'm talking about all the reference models. Fine. Who owns the internet? Please remember that internet is not owned by anybody. It is managed by some of these organizations. We mostly call them as standards organizations. If you see, there are many organizations which actually do this. If you say that all of these are open standards, the simple reason why we need open standards is interoperability. We don't want one vendor to take monopoly of the network. Now, if you want to buy a router, you can buy different versions of the router. All of them do the same task. All of them do the same thing that you want it to do, irrespective whether you are buying it for somebody else. You are buying it a Cisco, or you are buying it with Netlinks or Linksys or anything that you can talk of. Okay, so if you have an open standards, you can have interoperability with one another. You will have some competition, so that always the price is very competitive. And also the most important thing is the innovation. So if somebody comes up with new, or somebody might have a new idea, maybe a new protocol or a new type of service, everybody can implement it. Okay, so these standard organizations are actually vendor neutral. They are not owned by anybody. They are all from different people coming across the whole world, non-profit organizations, and they are established with the sole objective of developing and promoting the concept of open standards. So let me give you a brief account of all these standard organizations. Okay, so the top of the list, this is how the hierarchy is framed. On the top of the list is your Internet Society, also abbreviated as ISOC, which promotes the open development and evolution of the internet. And under it, we have an Internet Architecture Board, IAB, which is responsible for managing and developing these internet standards. So to do that, it has got two wings, or it has got two sides. One of them is your Internet Engineering Task Force, IETF. You must have seen a lot of IETF standardizations. IETF, which develops, updates, and maintains all the internet and TCP/IP technologies. They have different working groups which work on specific domains, maybe IoT, cybersecurity, cloud computing, like those kind of things. They have specific working groups. And coming to the Internet Research Task Force, the other wing, which is something called as IRTF, where we have once again they have steering groups. They do research in different areas, and once they come up with some new idea, they post it to the IETF, which is posted online. There is a different process where it has to go through a rigorous process. Then it will be assigned an RFC number. RFC stands for Request for Comment Series. So you will be assigned a number where many people can comment on it, and once it's approved, it will become an open standard. So along with these things, there are two other organizations which are very, very important for managing your IP addresses and port numbers. One of them is the ICANN, which stands for Internet Corporation for Assigned Names and Numbers. The other one is Internet Assigned Numbers Authority, IANA. So this ICNN coordinates the IP address allocation, the management of domain names, and assignment of other information. We'll study about the bodies which actually do these things in the module 7, which we discuss about the IP addresses in detail, IPv4 addresses. And the other one, as I told you, IANA, it oversees and manages IP addresses allocation, domain name management, and protocol identifiers for ICNN. This is how it works in the networking world. And if you see, there are also some other bodies which do the standardizations for hardware or physical components. The first and foremost of on the list is your IEEE, which stands for Institute of Electrical and Electronics Engineers. which is a body dedicated to creating standards in power and energy, healthcare, telecommunications, and networking. The other one is your EIA, Electronic Industries Alliance, which develops standards for electrical wiring, all the connectors that you're talking about, and the 19-inch racks, which are used for mounting the network equipment. And the third one on this list is the TIA, Telecommunication Industry Association, which is whose primary responsibility is to make sure the communication standards in the radio equipment, cellular towers, voice over IP devices, satellite communications, all those related to your telecommunications part. Fourth one is your ITUT, International Telecommunications Union, Telecommunications Standardization Sector. So this defines standards for video compression, internet protocol, IPTV, broadband communications, and DSLs. There is another body under ITU, which is ITUR, which actually defines the radio frequency standards for your cellular communications and all your wireless communications. On top of these are the different standard bodies. So these are the people who regulate your network or who manage and make sure that everybody is in order. Okay, so let's get on to the next part, which is the one of the most central components for computer networks, which are your reference models. So as you guys know, I have been telling that there is not just one thing that does all the job in a network. The network always does. The concept of computer network arises only from one question: how do I make one device communicate with another device? For this particular thing, I can't simply say there is one solution to do that. Okay, there are multiple problems which arise when you want to communicate one device to another. For that reason, what we did was we have taken this large problem and divided it into smaller chunks of manageable sub problems, and for these manageable sub problems we propose solutions. So each and every layer actually represents that one particular solution to one particular sub problem. Okay, so that is the concept behind layering, which gives you much more convenience to tackle the problems in a more efficient manner. Where if you want to solve one particular problem and if you want to change something, it does not have an impact on the entire network. You need not bring down the entire network. So complex concepts, how a network can, so for easier understanding and for easier tackling of the network, we go for a layered model. And there are two layered models which actually define the network operations. One of them is your OSI model, and the other one is your TCP IP reference model. OSI stands for Open System Interconnection Model, which has been defined and standardized by ISO. TCP IP reference model stands for the same. There are two protocols. TCP is one protocol and IP is one protocol. This reference model has been named from these two protocols itself. Okay, so let's go in and let's see what the protocols are or what the reference model is going to tell you. Now, what are the difference? As I said, what are the benefits of going for a layered model? If you said, there are some protocols which are actually operating at specific layers. They have defined information about how they act upon and a different interface to these layers to the and above and below. Now, a layered model or a layered protocol, a protocol in one particular, what it does is it actually provides services to the layers above it while receiving the services from the layers below it. We will discuss more about these things. And it actually increases competition between the different vendors, and technology capability changes. As I said, if you want to change something, if you want to do a modification in one particular layer or even one particular protocol, it does not need to impact the entire network model. And the last thing is one common language to describe networking functions and capabilities. So these are the different benefits of layered model. If I say to simply put these benefits, I will say efficiency and ease of usage. Okay, that is these are the two main primary benefits of going towards a layered model for networks. And these are the 7. Your OSI model does have 7 layers. These are the 7 layers that actually are stacked one on top of the another. You see, the bottommost layer is your physical layer. On top of it is your data link layer. On top of it is your network layer, followed by the transport layer, followed by the session layer. On top of the session layer is your presentation layer, and on top of it is the application layer. Here, each and every layer has a specific designed task. So let me start from the physical layer itself. The physical layer, as I told you earlier, it's earlier in my earlier videos, physical layer's main duty is to make sure to transmit the bits on the medium from the sender to the receiver. So if your physical layer's duty is to describe the means to activate, maintain, and deactivate physical connections, whatever connections are there, all come under the purview of your physical layer. Data link layer is mainly concerned with your frame transmission from one host to another host. So it describes methods for exchanging information or exchanging data frames over a common media. Your third layer is the network layer, which provides services to exchange the individual pieces of data over the network. The main responsibility of the network layer is routing and addressing. So how do you identify the devices on the network, and how do you route the packets or information from one part to another part so that it goes to the destination. Next comes your transport layer. Your transport layer actually defines the services to segment, transfer, and reassemble the data. So segmentation and reassembly is done here for individual communications. This is a much more like process to process layer. On top of the network layer is your session layer, which provides services like session management. So session start, if you want to set up a session establishment, session termination, session resumption, all these things are done by your session layer. On top of the session layer is your presentation. The name itself suggests to you, it presents the data in an acceptable format. So it represents the data for transmission. On the topmost is your application layer, where the user can interact with the network services. This is the layer which contains all the protocols which will help you for entering into the network or to communicate with the network. So these are your 7 layers of your OSI model, and the other reference model is your TCP IP reference model, which contains only 4 layers. Once again, the more or less the type of functionality of these layers remains the same. There is not much big difference between the functionality. Once again, application layer provides you the user interface. The transport layer provides you the communication between various devices. The internet layer provides you the path or the routing part or the addressing part. But the bottommost layer, which combines the functionalities of your physical and data link layer as well. So it controls the hardware devices and media that actually make up the entire network. So these are the 4 different layers of your TCP IP reference model. Okay. So let's go into the comparative part of the TCP and OSI. There are lots of comparisons. If you see, first and foremost, if I ask you, there are only 7 layers in OSI model, there are only 4 layers in TCP IP model. So the second difference might be, say, like if you see this diagram itself, the functionality of the above 3 layers in your OSI, which is like application, presentation, and session, are now combined into one layer, which is application layer here. Transport layer does the same job, whereas we call it as a network layer here, where we call it as an internet layer or internetwork layer. And once again, the bottom most 2 layers of your OSI model are now joined together to form one network access layer. More contradictory to the most common notation that OSI came first, TCP IP model has been first implemented. Later on, with the issues of interoperability and stuff, ISO defined the OSI model. But because of the because of the high popularity of your TCP IP model, most people are reluctant to move to the OSI model, and still we are using the TCP IP model that has been designed a long time ago in the 1970s. So these are the common differences. One most important striking difference is OSI model clearly defines the protocols, the interfaces, the each and everything in detail, whereas TCP IP model does not distinguish you much. In OSI model, the layers came first, and the protocols followed the layers, where it is vice versa in TCP IP model. In TCP IP model, the protocols came first and then followed by the layers. So these things most of the time you will be finding in your computer networks theoretical course. You can find lots of differences there. So please go to the internet and search for differences between these 2 models. You'll get much more information on these 2 models. Okay. So as we are discussing about this particular concept, what do you call data encapsulation? Data encapsulation is nothing but, as I told you, when the data moves from one point to another point, it has to go through a series of procedures. For this, we have 2 particular terms, something called as segmentation. Segmentation is the process of breaking up of messages into smaller units. We can't send a large message. It might not fit in your MTU. So for that reason, what we usually do is we take a large message, break it up into small parts, and then transmit it over. The other term which we come across regularly in networks is multiplexing. Multiplexing means if you take multiple streams of this segmented data and send it through the same medium, interleaving them, then that concept is multiplexing. Multiplexing is nothing but the ability to send multiple streams of data across the same channel. That's all. And segmenting is breaking up of large data into smaller parts. So why do we need to do this? Segmentation is simple. It increases the speed and it increases the efficiency of the entire network. So if you break it into segments, and if there is any problem with one segment of the data, only that segment needs to be retransmitted rather than sending the entire message again, which saves you a lot of bandwidth. Once again, increases speed also. When you're sending small segments, you can send it without bothering about all the links set up and all the MTUs and stuff. So segmentation is done for these primary to achieve these 2 primary benefits. Okay, we discussed this already. sequencing, where we actually put sequence numbers to each and every data frame that goes out. Sequencing helps you to identify the errors or damaged frames or even the duplication of frames that are being done. So sequencing plays a crucial role in networks. We'll discuss about these sequence numbers and stuff when we go into our further communications in the other modules. These are the protocol data units. As I said, when data moves from the upper layers to the lower layers, now this example gives you you should give you a very good idea. See, when let's assume that this is the sender who wants to send an email to the receiver. So it starts from here. As the email is quite large, what we did was we actually segmented the email into smaller parts. Now I have 3 segments of the same email. This is done at your application layer, so we still call it as data. Once it passes from the application layer to the bottom layer, which is your transport layer, if you see, this transport header is added to each and every data segment. Though I'm showing only one data segment here, this transport header is added to each and every one. Here, this particular PDU or protocol data unit is called as your segment. Now, if I may so, I can call this as TPDU, which stands for Transport Protocol Data Unit or Transport Layer Protocol Data Unit. So a TPDU is called as a segment. Now this is sent across to the, this is forwarded to the network layer. Here, this entire thing is considered as a TPDU, and the network layer adds its own header here. So this is also called as NPDU. Here we call it as a packet. NPDU, Network Layers Protocol Data Unit, we call it as a packet. Now this is now forwarded to the data link layer or the bottom part, where we add a frame header to it and also a frame trailer. Please remember the data link layer is the only layer which adds a trailer to your data. The information contained in your trailer is nothing but your frame check sequence, which is a CRC, where to make sure whether your frame has been received without any transmission errors or not. For the sender or for the receiver to verify this information, he can check it out this frame trailer which contains the FCS. So this concept of adding all these headers to the data at each and every stage is called as encapsulation. So towards the final layer, I mean, when it reaches the physical layer, irrespective of what it is there, it's only considered them as bits, because physical layer only talks in bits. It's only ones and zeros. So these ones and zeros are then transmitted across the media based on the type of the cable. If it is an electric media, you send it as electrical pulses. If it is an optical fiber, you send it as light pulses. And if it is a wireless media, you convert them into electromagnetic signals and then transmit them across. So each and every TPDU has a name. So your transport layer's TPDU's name is segment. Your network layer's TPDU name is packet. Your data links layer TPDU name is your data link layer's PDU name is frame. But the physical layer is just bits. Okay. So this process is called as encapsulation, and at the receiver side, you do the same reverse process, which we call it as decapsulation. Now we have come to the part where we want to learn about what are the different addresses are there and what is the role played by these addresses when you want to access the data from one point to another point, or when you want to move the data. So this comes under your network access part. It's the job of each and every layer on the reference model to make sure that your data is processed and delivered to the correct destination and also the correct application. For that reason, each and every layer adds some kind of specific information to satisfy that particular purpose. So if you see here, the most common two addresses that we use are the network layer addresses and the data link layer addresses. On top of it, we also have the transport layer who plays a part by assigning the port numbers, by identifying the port numbers and delivering the data to the port numbers. This bottom diagram will tell you what each layer does to make sure that the data is delivered in the right manner. So the upper layers, if you talk, there are some of the data is encoded along with your application, and whereas in the transport layer you see the port numbers. In the network layer you have the IP addresses, your IP addresses, which are also called as logical addresses. At the data link layer you have the physical addresses, which are your MAC addresses. And finally, the physical layer contains the timing and synchronization bits, which are added to make sure that both the sender and receiver are in sync, and to make sure that the data is received by your receiver. Now see here, I said to do this delivery, the most two common addresses that we use regularly are your network layer addresses and your data link layer addresses. The network layer addresses are your IP addresses, which you use. Unless until you have an IP address, your system will not be able to communicate with the internet. And similarly, the data link layer's address is called a physical address, which is a MAC address, which is embedded into your NIC network interface card, and it does not change. Your network layer address or your IP address keeps changing with your point of attachment. That means when you're at home, when you're connecting to your home Wi-Fi, you have one IP address, but you move away from it and you go to the college or somewhere else and you connect to that particular Wi-Fi, you will be assigned a new IP address according to that particular network. So the IP address is based on your point of attachment to the network. So through whose network you're attaching to, you will be assigned that IP address. That's why we call it as a logical address. Whereas the data link layer address, which is a MAC address, which is fixed, it comes along with your device. It is actually embedded into the network interface card. We call it as an Ethernet address also, but usually call it as a MAC address. So let's go and dig deep how we can identify what these addresses are. If you see the layer 3 logical addresses, as I told you, now check out this diagram. There is a sender here. There is a receiver here. So if you want to send some particular data to there, you have to have the IP address of the sender. This is a source IP address, and you have to have the IP address of your receiver, which is the destination IP address. Okay. Now in this, usually the IPv4 address is 32 bits in length, and it contains two parts. The first part is called as the network portion of it. The other part is called as the host portion. Now, before I go there, you have to understand the source IP address is the IP address of the machine who actually transmitted this message. The destination IP address is the IP address of the machine which actually finally receives this information, or to whom it is intended to. Those are your source IP address. This is your destination IP address. And once again, in each and every IP address, we have two parts. The first part is a network part. The second part is your host part. The network part will actually tell you to which network it belongs to. Now, if you are in your home and you have maybe 2 or 3 mobile phones, laptops, all these things connected to the same network, all of them will have the same network portion because all of them belong to the same network. But each one will have a unique host portion so that we can uniquely distinguish one device from another device, or it will be needed to identify these devices. Similarly, in IPv6 version, we have the prefix part and we also have the interface ID part. So your prefix part does the same job as your network portion. Please remember that if you are having a particular LAN or a WAN, all of them, if they belong to the same network, the network portion will be common, whatever the network part might be. Whereas in the host portion, the host portion is unique for each and every device. Unless until the host is unique, you will not be able to identify that device. So these are your logical addresses. Remember that host portion and network portion, we will be requiring it a lot when we discuss about subnetting of IPv4 and also IPv6. This plays a crucial role because not all the, if you say 32 bits, you cannot simply say that sir 16 is network and 16 is host. There is no way to specify like that. There are some ways which is called legacy addressing, class full addressing, which used to do that in that particular manner, but it is no longer being used. We are using, that is the reason we actually specify a subnet mask so that the machine can understand which part is the network address and which part is the host address. Now, if you go in depth, what if you say the devices on the same network? There is a system, there is a user sitting here and there is another user sitting here. All of this belongs to one particular network. If you can see, there is a router here, there is a router here, and there is a switch here. So let us assume that this is all belonging to the same network. Now, if you check carefully, this network portion in both the IP addresses is the same, 192.168.1. And if I say, sir, there is another person sitting here, if I take one, this is another person sitting here, he will also have the same 192.168.1 prefix only. But the remaining part, which is your host portion 110.9, it has to be unique. Otherwise, if it is not unique, we won't be able to identify which particular machine we are using. This part will tell you that all these people belong to this particular network, this person, and even the FTP server, which is sitting over here. Okay. Now, sir, then if I want to transmit the data within our own network only, if you check out here, this address which is bottom is your MAC layer address, or it's your MAC address, which is 48 bits in length. It is 48 bits in length. This is your MAC address. You see, it will show in within the, as I have been discussing about the encapsulation process, right? So this encapsulation process, I told you that each and every layer adds a header to the data. which will help it during the decapsulation process and to process this particular data. Now, if you check out the IP header, if you says that the source is your 192.168.1, which is your network portion, and the host part is 110, and the destination IP address will be to the same thing. So whenever any person sees this, they will understand that the network portion is the same. So this packet is to be routed within the same LAN. Then how do you distinguish? The distinguish comes here. If you see, the destination MAC address is this, whereas the source MAC address is this. Okay. Please observe that any device which belongs to the same network will have the same network path, but will have a unique host path. Now let's move on. If you see, what is the role of the data link layer addresses if you are within the same IP network? Now, as I told you, we just discussed that the source MAC address will be that of the originator of the link, whereas the destination MAC address will be that of the destination on that link. Whereas if you see, MAC addresses are physically embedded and they are local addressing only. Only your data link layer is able to understand your MAC addresses. So a switch cannot read them and forward them within your network. Now, what if, sir, what is the role of the network addresses? When the source and destination have a different network portion, check out this diagram. Now we are actually, if we want to communicate, this person wants to communicate with this particular server, which is in a completely different network. So how do you say this is a different network? If you check it out, this has a different network portion. This has a different network portion. So automatically I can understand, I can infer from looking at saying that, okay, it is different. What do you do, sir? So if a packet now is going from here to there, the network layer now prepares the packet header in such a way that it shows that this is the network portion of the source, this is the host portion of the source, and for your destination, this is the network portion, and this is the host portion of your destination. It means that I want to communicate with the server. You can clearly see that now the packet has to travel from this network to this network. It has to move between networks. Earlier, it used to be in the same network. So now, what is the role of the data link layer addresses if you are having a different IP networks? Earlier, I told you that these data link layer addresses are actually read by your data link layer, and they are only confined to layer 2 or your switch within your own network. Now, what if you want to communicate from here to this particular web server? If you check it out, the source MAC address will be the same from which you are sending, but here the destination MAC address now belongs to the router which you are connected to, or the interface of the router to which you are sending it out. Here we actually come across the concept of something called as a default gateway, which I haven't covered yet now. Default gateway is the router IP interface which acts like a door for any network that wishes to go outside of this network for any data. Let me repeat that again. The default gateway is the router's interface which acts like a door for any data that wishes to be going or that wishes to travel to another network. If we take this as an example, if this person, let us say if he is A, this is B, this is C. Now, if these three devices wishes to communicate within the same network, you will not need a default gateway. There is no reason for it because they can communicate within the same network. But if A wants to communicate with D, this D is situated completely another network, right? This does not belong to the same local area or same LAN. So for this to happen, we have to specify a default gateway. This is also there in your IP address settings. Because we still didn't cover it, I didn't tell you in your earlier video. Unless until we specify the default gateway, the packets within this network does not know where to be transmitted to. That means once I specify this particular interface address as the default gateway, now A's packet can be routed to this router. From there onwards, it will take this path and then finally delivered at D. If I don't do this, they don't know where the door is. If they don't know where the door is, they will not be able to get out of this network. They will only be doing within this network only. So only intra-network communication only will be happening. So now when I specify this default gateway, now we have to specify the default gateway for the switch also. Please remember that default gateway is always the IP address of the interface of the router to which you are connected to. So for all these devices, the default gateway will be the IP address assigned to this interface of the router. If you see, when the final destination is remote, layer 3 will provide, layer 3 means your network layer. Layer 3 will provide layer 2 with the local default gateway IP address, also known as the router address. Here some people also might, if D wants to reply back, now once again, because A is in another network, unless until you specify the default gateway address of this interface on this switch and also on D, they will not be able to reply back to A. So the default gateway plays a very crucial role if the devices wanted to communicate to another networks or to remote networks. Within the same network, you need not require it, because you will simply look at the MAC address and can send it through. Now here, the source MAC address, so what are you going to put the destination MAC address when you are transmitting to another network? The destination MAC address now belongs to the router's MAC address. Okay. As I said, all devices on the LAN A, B, C must be told about this default gateway address. Otherwise, they will not be able to communicate to other networks. They will only be confined to communication within that network only. Okay, so this is very crucial. This is very important to understand the concept of default gateway here. If you don't have a default gateway, you will not be able to send data to another networks. We will work on the default gateways assignment in our further packet tracer activities. We'll do that. How to assign it. This is the same simple command, but you have to understand which default gateway address you have to do, and also during submitting, which will become your default gateway address. Now these are the data link addresses. If you see it here, if you check it out, this particular diagram, it says that PC1 wants to communicate with the web server, which is in a completely different network. So what is the role played by these layers and what type of address are being added? Once it starts the journey from PC1, you will have a layer 3 header and you will have a layer 2 header. The layer 3 header will have the IP address of your source and the destination address of your web server. Now, once it is passed down to the data link layer, this will have the destination NIC as our MAC address of this particular PC1, and the destination is the MAC address of the router, and the source will be the MAC address of the PC1. Now it is forwarded to the router. Here once again we test whether the data has been received in the correct order or not, and the router will identify the destination IP address. It will know that now in order to forward to this destination IP address, it has to forward onto this link. If you check out, the layer 3 packet remains the same. We are not going to change anything with layer 3, but there are 3 colors given for L2, simply because here for this particular packet, what we will get is, in this L2, the destination NIC will be the MAC address of this router, and the source NIC will be the MAC address of this router in this particular hop. Now, once again, if you move on, this receives the same packet, once again does the same analysis, checks out to which network it has to forward it to. It decides now it has to forward it on this link. And now once again, it changes the data link layer address, simply because now the source the source MAC address will be this router, and the destination MAC address will be that of the web server. Please observe that in any of these hops, the layer 3 packet is not going to be changed. Only the data link layer address. That is the reason why I told you in the very first class itself, data link layer is called as a hop to hop layer. So at each and every hop, it makes sure that the data is being transmitted in the correct manner or not. Are there any transmission errors? All these things will come into play. The network layer is a source to destination layer. That means, so this will specify which is the source, and this will specify which is the destination. This is how it usually happens with these addresses. And if you check it out, the second hop, this is what I just told you. So this is how the first router exit interface and the second router interface, at each and every point, what we'll do is this layer 2 addressing will be keep on changing. So here it says the source will be this particular router and the destination will be this particular server. This is how it usually happens. The layer 3 address or the layer 3 headers will not change. Okay, hope you understand this. This is very easy concept, guys. So it says a lot of diagrams over here. Please do not get confused. It's nothing to get confused here. It's pretty similar and it's pretty straightforward. If you're sending it at each and every hop, the data link layer checks and updates the header accordingly with this appropriate source and destination. Whereas your layer 3 packet will tell you what is the actual source, what is the actual destination. Data link layer source and destination is related to your hop. So first, this is your original source, this is your original destination. For this hop, this is the source, this is the destination. For this hop, this is the source, this is the destination. And in this hop, this is the source and this is the destination. Okay, the L3 addressing remains the same since it is global and the ultimate destination is still the web server. Whereas local logical or your data link layers are local in nature. That is the reason for each and every hop you keep on changing the addresses of your data link layer. Okay, so with this we will stop your module 3. Hopefully everybody has understood this. The most important takeaways from this particular thing are your the most important takeaways, as I said, are from this module are your protocols, your reference models, layering, addressing. The remaining ones we will be as there is a one packet tracer activity which actually shows you how the OSI model works or how the layers are being added, what is the information that are present in your layers. I will make a video to demonstrate the packet tracer activity. Meanwhile, just go through this because this is a very important particular module, simply because it covers all the fundamentals and basics of layering reference models. So guys, hope I did a good job. Thank you very much. I'll come back with the module 3 packet tracer activity. Thank you very much. Have a nice day. Bye.